Okay, class has begun. Welcome to physics for September the 10th. And also I'm going to use this recording for September 11th as well. My B-Day class, I'm going to have them watch the recording rather than doing it live. So if you're in the B-Day class, hello. And come to think of it, if you're in the A-Day class, hello too. All right, in a few minutes, I'm going to go over the homework. And I will take questions about the homework in a few minutes. But what I want to do before we talk about the homework is I want to just do a quick check to see if you understood the homework. What I do is I give 2 scores each day. One score is what I call a completeness score. So if you turned in your homework and you did the majority of the problems, even if you didn't do them all right, I'm going to give you a 10 for the fact that you turned it in. Okay, so I call that a completeness score. Now, if you didn't do all the problems, then I won't give you all 10 points. Mr. Hendricks being nice, yes, that's pretty scary there, isn't it? Okay, so you get 10 points for completing the majority of the homework problems, even if you didn't do them right. But it's important that I somehow measure whether or not you actually understood the homework problems. And so that's what I call the comprehension score. And the only way to measure whether you understood the problems is to take a quiz. So Sam, you might want to take back what you just said about me being nice. So we are going to take a quiz today. Some of you may have already noticed that the quiz is in Canvas. It was just locked up until about 1 minute ago. It is now unlocked. What I want you guys to do is to stop right here. I'm going to stop the recording even. And I want you to go into Canvas, open up the quiz, and you will find that as soon as you open it, you're only allowed 5 minutes to finish it, but 5 minutes should be plenty. The questions are really quick, and I think they're simple. So everybody do that right now. Go into Canvas, take the quiz, and then when you're finished, come on back here. I'll be waiting for you. And those of you that are in the B-Day class who are watching the recording here, I would like you to do the same thing. I'd like you to go take the quiz before we talk about the homework. So please do that. Sam is saying, curse you, Hendricks. Good. It's good to know that my reputation for being mean is still intact. All right, go take the quiz. I will pause the recording. All right, I just started the recording up again. I see there are still 3 people left who haven't finished it. I'll give you just another minute. Okay, 1 more person still needs to finish it. Okay, still got 1 more person to go. Okay, looks like everybody's finished. Let's talk about it. So in the chat box here, I see lots of people saying that they didn't feel that they did the quiz as well on the quiz as they would have liked. Don't worry. Hopefully you remember from reading the disclosure statement at the beginning of the school year, I allow you to retake quizzes. But it's important for me to look at how you do the first time around, because that gives me feedback on what are some things that I need to do differently. What do I need to reinforce? And so looking at these results here, I can see that, yeah, some of you still are a little weak on sig figs. We'll spend a little more time on sig figs. Remember, everything that we do all year long, you always have to report the answer with the right number of sig figs. And so just get used to that. Now, I am going to allow you to retake this quiz, but not right now. You may have noticed I've got Canvas set right now, so it only gives you one shot. But later on, after I've gone in and looked at your responses, I will open it back up. I will allow you to retake it. But it's really important that you understand that if you retake a quiz, you have to send me an email telling me that you've retaken it, because I do not link Canvas automatically with Aspire the way that many of your other teachers do. I've talked with those other teachers and they've told me horror stories about times where the link doesn't quite work right and the grades sometimes get transferred and sometimes don't. And so they can't really trust that the grades are getting transferred properly. And I will not accept that. So I transfer them manually. And therefore, if you go back in and you retake a quiz, if you don't send me an email telling me that you've retaken it, the new score will not get transferred into Aspire. So make sure you do that. But give me a day or so, because what I want to do is I want to go in and look at your first quiz results, and that will be very important information for me. So in about a day, I will reopen the quiz and I'll allow you to retake it, but not for another day. Okay, other questions about the quiz? Everybody's good on that? I should have turned on my video all that time there. All the time I was talking, my video was off. Okay. Now let's talk about last night's homework. Let me go into a presentation I've got here. All right, here are the answers to last night's homework. First off, you're going to notice that I have not put all of the answers up there. I've only put the answers to the even number problems, because I'm trusting that you have already gone in and looked at the odd number problems. And I want you to do that. It's not cheating for you to look in the back of the book. I want you to look in the back of the book. That will help you as you're going along so that you know whether you're getting it or not. So look back there, but before you look in the back of the book, work the problem first, okay? Don't just go right straight to the back of the book. That doesn't help anybody. Work the problem first, give it your best shot, then look in the back of the book and see if you got it right. But you won't be able to find the even number going back there. All right, so I'm going to pause for a minute. Yes, yes, the back of the book does have answers. Maybe you weren't here when I said that. Any questions about the homework? Yeah, I don't have time to go over every single homework problem. I will not ever plan to do that. I can take time to go over 2 or maybe 3 of the homework problems, but that's it. So you have to tell me which ones you want to go over, if any. Not hearing any questions. Does that mean that you guys feel really good about it? Let's see. Oh, I'm looking at your quiz scores here. Your quiz scores, some of them are very good, but some of them not so much. Well, how about if I pick a couple? If you guys don't ask questions, I'll ask a question. How about problem number 8? Let's take a look at problem number 8 and let's do problem number 8 together. All right, so I see a couple of you are saying you don't know what questions to ask. Well, okay, I will ask them for you. All right, let's look at problem number 8. Let me open up a white screen here. Okay, so problem number 8 is saying we want to convert 5.3 meters per second into kilometers per hour. All right, let's see how we do that. Actually, how about if I pick on a couple people here? Who should I pick on? How about Krista? Would you be willing to help us do this problem?
Sorry, can you say it again? There was an ambulance that went by.
Oh, all right. So could you talk us through how to do problem number 8? So I'll write on the board here. So what we've been given is the number 5.30 And that number is in meters per second.
Yeah.
So they want us converted into kilometers per hour. How would we do that?
So I put in parentheses, I put 1 km over 1000 m.
You guys agree? 1 kilometer. Oops, hang on. Try that again. Okay, so 1 kilometer is 1,000 meters. That's a conversion factor that you should all know. Now, Krista, before we go on, if we're following the Ames method, and especially the Hendricks version of the Ames method, what must we do before we go on?
Cancel out.
We cross out the units. So we look to see we got meters on top, meters on bottom, they cross out, good. It's because it's really easy to mess up. I mean, a lot of people put 1,000 meters on top and 1 kilometer on the bottom. And so if you don't cross out the numbers and see, yeah, we got meters on top, meters on bottom. If you don't cross that out, it's easy to make a mistake. Okay, so looking good here, Krista, except right now we've got it as kilometers per second. We need kilometers per hour. What do we do next?
And then I put another parentheses, and then I put 3,600 seconds over 1 hour.
Okay, very good. Now, some students don't know where that number comes from, so I hope you don't mind if I do it in 2 steps. What I'm going to do is I'm going to say there's 60 seconds in 1 minute, and I see seconds on top, seconds on bottom, so I know that I did it right. So now we got kilometers per minute, but we need kilometers per hour. So we do it again. This time there's 60 minutes in 1 hour. Okay, so minutes cancels minutes and we're good. Okay, so what Krista did was the same thing because 60 times 60 is 3,600. All right, so what do we do now, Krista?
And then I combined them all, I guess.
Yeah, that's a good way to put it. Okay, so we're gonna take all the numbers. We're gonna take 5.3 times 60 times another 60. We're gonna divide that by 1,000, right? Now, Krista, when you did that, I want you to tell me what number your calculator gave you. Let's worry about sig figs later. What number?
Hold on, I didn't,
I'll tell
I
you
got
what,
9.
I've got it in front of me right here. I'll just tell you. So when I do it on my calculator, we get 19.08.
Yeah, that's
So
what
Krista, is that the number I write down as my answer?
No,
Why not?
because you need the right amount of sig figs.
I need the right number. Yeah, sig figs. Don't say it with a question mark in your voice. Say it with an exclamation mark in your voice. Say, you need the right number of sig figs. Okay, now the question then is how many sig figs are we allowed? So let's go to somebody else here. How about Dylan? Dylan, how are we going to determine how many sig figs we're allowed?
Isn't it by the original number?
Sometimes yes, sometimes no. I mean, the original number has 3 sig figs. I'll agree with that.
Yeah.
But if you look at this number right here, the number 60, if I just write the number 60 on the screen and you don't know where it comes from, how many sig figs would you say there are?
2? No, 1. Yeah.
Right. If I just write the number 60 and you don't know where it comes from, that would be 1 sig fig. So the number 60 that we have on our screen right now, is it 1 sig fig?
Yes.
Okay.
Right.
I want everybody to type into the screen here. Let's take a vote. How many think that that number 60 that we see on our screen right now, we should treat it as 1 sig fig? And how many of you think that we should treat it as something different? Come on, I need some, okay. All right. Okay, Connor, why are you thinking it should not be 1 sig fig?
Because you know that it's an exact value and has infinite sig figs.
Okay, what he said is exactly right. We look at this conversion factor right here. 1 minute is not approximately 60 seconds. 1 minute is defined to be exactly 60 seconds. All right, so this 60 that we see here, that has an infinite number of sig figs in it. It's a defined quantity. The other 60 on the right is the same thing. And also the 1,000 down here. You know, 1 kilometer is not approximately 1,000 meters. It's defined to be exactly 1,000 meters. All right, so we don't worry about these guys when we're talking about sig figs. Therefore, the only number that we have that actually has sig figs in it is in fact the number that they gave us. And there are 3 sig figs in that. Be careful, you guys, that 0 at the very end there, that 0 is not necessary as a placeholder. You know, if we wrote the number 530, okay, then the 0 would be a placeholder, and then it would be not significant. But that 0 that we have is on the right side of the decimal, okay? It isn't necessary as a placeholder. 5.3 is basically the same number as 5.30, all right? So we didn't need that 0 there as a placeholder, but we put it there anyway, or at least whoever wrote the book put it there. So they must have had a reason for putting it there, which means it is significant. So 3 sig figs is the right amount. So what that means is that we have to take our answer here, 19.08. We can't write that as our answer. We have to round it off to 3 sig figs. Therefore, the answer here is 19.1. Okay. All right. So let's go back. Okay, so that's where the 19.1 came from and why it's not 19.08, right? So I see a couple people typing into the comments here saying, whoa, this is mind-blowing. Well, we talked about this last time, guys. This shouldn't be a surprise here. I'm willing to take time to answer one more question if anybody has another question. If not, I'll jump into the new stuff, but I'll give you another few seconds. Speak now or forever hold your peace, or actually just speak now or ask me later. Now, I realize that some of you might be reluctant to ask questions because you know that this session is being recorded and you don't want to be recorded asking a potentially embarrassing question. So if that's the case, I understand. At the end of class, I'll turn off the recording and then we can talk and you can ask any embarrassing questions that you want. Okay, last chance. Questions? Yes, no? I'm not seeing any. Okay, well, in that case, let's move on to tonight's material. We are going to start into chapter 2 now. Some of you might say, but wait, Mr. Hendricks, there are a few pages from chapter 1 that we didn't talk about. Well, I didn't talk about them because I didn't think we needed to talk about them. The last part of chapter 1 talks about how to do graphs and using error bars and measurement precision versus measurement accuracy. And I think we pretty well adequately covered that in the flat earth activity. You guys showed me in the flat earth activity that you know how to do graphs and you know how to take equations and fit them, and you know how to do error bars and decide about how much precision you can put in your graphs. So I'm thinking we're done with chapter 1. Therefore, let's go ahead and jump right into chapter 2. Chapter 2 talks about different ways that we can represent motion. Because in physics, we're going to be dealing a lot with things that move. We're going to study things that move. We're going to study why do they move. And so first thing we have to do is figure out different ways that we can represent motion. All right. One very common way to do it, a way that's nice and easy to understand, is called a motion diagram. Also, sometimes people call it a dot diagram. And I think this illustration here does a pretty good job of showing how it works. Let's suppose that we got somebody running by and we're sitting here with a video camera and we take a frame every 1 second, which is pretty slow for video. Normally video is like 30 frames per second, but okay, so we're doing 1 frame per second. When we take the first picture, the runner is right here. That dot doesn't show up very well. Let me try maybe black, see if that shows up better. All right. And then 1 second later, the next frame shows the runner has moved over to here, 1 second later over here, second later over here, and then here. Every 1 second that goes by, the runner appears in a different frame. And hopefully from the picture here, you can see, well, if they move 5 meters in that second, then they must be moving at a speed of 5 meters per second. And so what we do is we either put a dot right on the runner, or what we will sometimes do is we'll not even include the runner at all. We'll just put a dot right there. And if these dots are all evenly spaced, then we know that the runner is moving at a constant speed. But that's boring. So let's do something a little more interesting. Let's suppose I have a dot right here. And then 1 second later, I have a dot here. And 1 second later, I have a dot here. 1 second later, I have a dot here. And then 1 second later, I have a dot here. So let's see, how about Vian, would you please unmute yourself and tell me what's happening here? Why are the dots no longer evenly spaced?
Probably the speed is fluctuating, so it's not staying completely constant.
Okay. Is the runner speeding up or slowing down?
They're speeding up.
Okay, don't say it with a question mark in your voice. Say it with an exclamation mark in your voice. Yeah, they're speeding up. Okay.
They're speeding up.
Very good. All right, that's the spirit. Okay, and let's try another one here. All right, let's suppose we got a dot here, and then another dot here, and then the next dot is here, next dot is here, next dot is here, and then we have a whole bunch of dots right on top of each other, and then we have a dot here, and then a dot here, and a dot here, and a dot here. All right, let's have Zainab. Can you unmute yourself here and tell me what's happening? Oh, okay. Sorry, Zainab isn't here today. I forgot. Miriam. Miriam, can you unmute yourself and tell us what's happening?
This time the person's slowing down.
All right. So in the first half of the picture, I agree, they're definitely slowing down. So they started out here going fast. Okay, and then they get slower and slower and slower. What happened here, Miriam, when we have all the dots on top of each other? What's the deal there?
They probably stopped.
Not just probably stopped, they definitely stopped.
They definitely stopped.
Yeah. Okay, but now the darts start up again, and they're close together, and then as time goes on, they get further apart. So what does that mean there, Miriam?
Speed it up.
Yeah. All right, so somebody was running along, they slowed down, stopped, and then they stayed there for a while, and then they started accelerating again. Now, one big problem with the motion diagram or the dot diagram is during the time that they were stopped, all of those dots are right on top of each other, and so we don't really have a good way of counting the dots, and therefore, if I were to ask you how much time the runner stood there not moving, we don't really have a way to tell by looking at the motion diagram. If only there was another way to represent motion. Well, it turns out there is. Yes, if only. Turns out there is. But before I talk about this other way, let's talk about one other thing that's really important about the motion diagram. Where do you draw the dot? Okay, now what we see here is a bird. And if I wanted to be contrary, then I might draw the dot on the wingtip. So there's a dot there. And the next one, there's a dot there. And the next one, there's a dot here. And then finally, there's a dot here. And I could, in theory, do that. But it's going to be confusing because if you look, these two dots reasonably close together. These two dots are a lot further apart. So since the dots are getting further apart, that makes you think that maybe the bird is accelerating. And the fact that the dot is going from low place to a high place, that means that, and then high place back to low again, looks like maybe the bird is going up and then down. But is the bird really going up and down, and is the bird really accelerating? Well, I think you guys can tell the answer to that one is no. So clearly, putting the dot at the end of the wingtip there is a bad idea. So how about Jackson? Where would you recommend we put the dot? Earth calling Jackson.
Sorry, my mic was muted, but I
Okay.
was talking.
Okay.
Anyways, I'd say you put it down again.
Down where?
Like, down past the other dot, like on the right.
Yeah. Well, here's what I would say. We should find a place that's called the center of mass. Some people call it the center of gravity. I don't want to go into distinctions. There are minor distinctions between the two. We'll save that for later. We will talk about that later. So the center of the bird, the center mass. So if we put a dot there and a dot there and a dot there and a dot there, now you can see the dots are in fact evenly spaced. There's no funny up and down motion. So when you're doing your motion diagrams or your dot diagrams, make sure you draw the dot in what we call the center of mass. That'll make things so you don't get confusing. All right, so that's a motion diagram. One other thing I want to talk about, now motion diagrams are really good for helping understand the difference between these two words that a lot of people sometimes don't know the meaning of. So we've got two words that we are going to be using a lot in this class: position and displacement. You need to know the definition of those. All right, position is defined as where is the object located relative to some origin. Now, the person who drew the picture here, they chose their origin right here. And so if I were to ask you, what is the position of the runner at t equals 3 seconds? Well, you know, this is 0, this is 1, this is 2, this is 3. So here is the position. So at 3 seconds into our run here, the runner is 15 meters away from the origin. Now, if I were to draw an arrow, which by the way, we're going to be doing lots of, these arrows here are called vectors. So if I were to draw the position vector, it would be the arrow that starts at the beginning. It starts at the origin and it ends at wherever the object is at whatever time I'm interested in. So that red arrow that you see right there, that is the position vector for the runner at t equals 3. But there's nothing magical about that particular choice of origins. If I wanted to, I could choose a different origin. So let's suppose that Sam comes along. She likes to be different. And Sam says, I don't like my origin right there. I want to have my origin right here, wherever this pole is. So then how would Sam draw the position vector? So Sam, you want to unmute yourself? So if you define your origin to be there, how would you draw your position vector?
Okay, so my place of origin is at the 25 mark, right?
Yeah, at the
So
pole
then
here.
I would just, well, yeah, okay.
Okay.
So I guess I would draw a dot at my place of origin, which is at the pole, and then move it forwards towards like 30.
Well, let me do that a little differently. The runner is in this place where I've got him circled. I mean, the runner is where the runner is. Irrespective of where we draw our origin, this right here is where the runner is located. So if Sam were to draw her position vector, because she's got a different origin, her position vector starts in a different place, but it points to wherever the runner is at that given time. Whereas Jackson, he's more of a traditional guy, and he says, no, I'm okay with my origin back here. So if Jackson draws the position vector, he's going to draw it like that. So you see that Jackson and Sam both draw different position vectors, and that's okay. This is Ames. We are accepting of people who like to do things differently. That's perfectly okay. All right. So the position vector depends on where you put your origin. Now, let's talk about something called the displacement vector. All right. Displacement, as you can see down here at the bottom of the screen here, displacement is defined as the difference between the final position and the initial position. Or another way to think of it is that displacement, which they have written here as delta D, and I've got some windows Zoom is a nice thing, but it gives me all sorts of windows that you guys can't see. And sometimes those windows get in the way. All right, so I've moved them out. Okay, so delta D is what the book is going to call as displacement. If I take that, so if actually tell you what, let me do this a little differently here. Let me start off with I'm going to start with my initial position. So that's going to be DI. And let me get rid of this arrow here. Oops. All right. So if I take my DI and I add my displacement vector, which is what the book calls delta D, that will give me my D final vector. All right, so let's suppose that we are Jackson. We're a nice conformist here. And so this is our position vector at the beginning. So I'm interested now one thing I didn't make clear here, I'm interested in the displacement from the time t equals 3 to the time t equals 4. That's important that you understand that. All right. So let's see, Jackson is going to do then is he's going to say, okay, well, my initial position vector is this, and my final position vector is this. So my displacement vector then must be the vector that starts where the object was at t equals 3 and goes to where the object is at t equals 4. So that brown vector right there, that is the displacement vector that Jackson is going to draw. But what about Sam? Okay, Sam says, oh, Jackson, you drew your position vector wrong. Your initial position vector is really this, and your final position vector is really this. But what about the displacement vector that Sam draws? Okay, do you see that it's going to be the same? Because the displacement vector always has to start from wherever the object started out at, regardless of where your origin is. And it ends up at wherever the object ends up at, regardless of where the origin is. So you can see that even though Sam and Jackson are going to draw different position vectors, they're going to draw the same displacement vector. Does that make sense, everybody? I'm not hearing any complaints, not seeing anything in the chat box. Are you groaning in pain there?
No, I'm just trying to process this. So position is like 0, 5, and like where your origin is, but displacement is how much you move.
Okay, let me just rephrase that ever so slightly. Okay, position is where are you relative to the origin? Or in other words, let me rephrase that. Position is how far are you away from the origin at any given time. Okay?
All right.
Displacement, we don't care where the origin is. All we care is where were you at the start of the time period that we're interested in, and where did you end up at the end of the time period that we're interested in it. So what I have to do is I have to specify a time period. So I have to say that I'm interested in the time period in between t equals 3 and t equals 4. Or I might say the time period in between t equals 2 and t equals 7. So I have to give you two different time values in order for you to calculate displacement. But I only need to give you one time value for position. All right. So not hearing anymore. Let's go ahead and move on. So remember how I said that the dot value or the dot diagrams, the motion diagrams have one serious drawback. They don't let you know when or how long the runner was stopped. Okay, so what I have here is a different way of representing motion. And this is called a position versus time graph. And you should have seen these in your math class. Should not be anything new and exciting here. So what we have here is a race. And so this is a car race. And you can see we got 3 cars. We've got car A is the solid line, car B is the dotted line, car C is the dashed line. And what we've done is we've graphed their position as a function of time. What I want you guys to do is I want you to pretend that you live back, in many, many decades ago, back before television was invented. And so you and the family are all gathered around the radio and you're listening to the announcer as the announcer describes a car race. And if you've ever seen this on an old time, on a movie about old times, you'll notice that generally the announcer, they start off by saying, and they're off. Seabiscuit's off to an early start with the Secretariat close behind. As they round the corner, Seabiscuit trips. Secretariat just stepped on Seabiscuit's head. Oh, there's blood everywhere. Oh, how horrible. Okay, so we need some sort of a, yeah, those are the names of horses. You are correct. So this is a car race, not a horse race, but that's okay. The same idea still applies. All right, so here's what I want you to do. I want you to pretend that you are the announcer, and I want you to focus in. We're going to take this a chunk at a time. I want you to focus in on just the first 5 minutes of the race. Ignore the rest of it for now. We'll come back to it later. Just focus in on the first 5 minutes of the race. Take a few seconds and think about what you would say if you were the announcer. And the graph here is describing the position as a function of time. So you need to think what could be explaining that. And so then you're going to be the announcer. So I'm going to give you just 5 or 10 seconds to think about it. And then I'm going to pick on one of you. And I want you to unmute yourself and be the announcer. All right, I think you've had enough time. So Gia, you win the lottery here. I want you to unmute yourself and I want you to be the announcer for the first 5 minutes. Okay? Gia, are you there?
Okay.
Okay.
I guess start off with, wait, how do you start off on the radio thing again?
And they're off.
And they're off. Car A takes the lead, and car C, stays in the back, I guess.
You got to think up some reason. Why do you think car C is not moving?
Maybe car B crashed into car C.
That's possible.
Yeah.
Yeah. What makes you?
It's not moving at all.
Yeah, car C is not moving at all. Now, what makes you think that car B might be having some sort of trouble? I mean, you say that it crashed into car C. What is it that tips you off the fact that car B's got something wrong with it?
Well, car A is still ahead, so I'm assuming that car A is having nothing going on.
Okay, so you're recognizing that car A is going faster and it's in the lead, car B is in second place, and something is wrong with car C. All right, so Gia is thinking maybe it's because car B maybe hit it right at the very beginning. Okay, that sounds good to me. All right, let's move on now to the second period. So in between t equals 5 and t equals 10. I need somebody to speak up. How about Aurora? Would you be willing to unmute yourself and tell us what you would say if you were the announcer looking at this?
Yeah, give me a second.
Okay.
Looks like car C has recovered from his stallation at the beginning. He is off at a pretty constant rate, while as car A keeps going its pace. But looks like car B earns a bit of its speed back, shifts gears, and is running up on car A.
Okay, very good. Now, Aurora seems to think that car B is now going faster than it was during the first 5 minutes. What is that correct, Aurora? Is that what you think? And if so, why do you think that?
I think he is because he like the graph, it like goes at a steeper incline, and so yeah.
Okay, so let's talk some mathematical language here. It sounds to me like Aurora is looking at the slope of the line. Ooh, that's terrible. Let me try that again. Okay. Oopsie, hang on a second. Okay. All right. Aurora is looking at the slope during the second time period, comparing that to the slope during the first time period, and she's saying the slope has increased. Therefore, she thinks that that means that the speed has increased. Make sense? Yeah, I'm thinking she's on to something there. Okay, good. All right, Aurora, can you think of some reason why car B might have sped up?
I think that possibly he could have like, if you understand like the cars, he probably like could have shifted gears, which would have like boosted him, you know?
Ah, okay. So for the first 5 minutes, he was going along in the wrong gear, and 5 minutes into the race, he said, "Oh my goodness, if I just shift gears here, maybe I can go faster." All right, I like that. Or maybe this is Mario Kart. You guys, in Mario Kart, they have all these little diamonds or whatnot lying around. And if you pick up one of those diamonds, you get a speed boost. Who knows? Maybe it's something like that. Okay, great. Let's move on now to the next time period. So this is the time period in between t equals 10 and t equals 15. Who gets to win the prize here? How about Amy? Would you be willing to unmute yourself and you be the announcer for the next 5 minutes here?
Oh, uh, I feel like I'm on the spot. Like, oh gosh. Okay. So I'm just supposed to like kind of explain like about like
Well, you're the announcer,
the oh
all
gosh.
right? So
Why
as
me?
you probably noticed, at about 11 minutes into the race, something weird happened. Can you think of anything that might explain that part that I just circled?
Okay. So what happened was that at 11 minutes they realized that there was an old lady passing by, so they decided to stop. But car C just decided to keep on going and kill the old lady.
Well, we got a gruesome bunch of people here. Okay, all right, interesting. Can you think of anything more you want to say about it, or you can call that good?
I'll call that good. I'm proud of my answer.
All right, well, I like the answer. How about Calvin? Do you want to elaborate? Can you think of anything that you might come up with for what happened at, let me clear the drawing here. So at this point right here, that's the point that I'm really interested in. So Calvin, could you come up with an explanation for what happened there?
Yeah, sorry. I think that car B was getting really close to car A and maybe tried to like tap it to get it out of the way, or like spin it out possibly, but they messed up and it probably like hit their wheel, and that's why they're going constant for the rest of the time.
Okay, interesting. All right. So it sounds like Calvin is saying that 11 minutes into the race, car A and car B are at the same position. So Calvin is suspicious that maybe they actually crashed into each other, which certainly could explain it. Now, there could be other explanations. I mean, Amy's got an interesting spot. Maybe there was some old lady standing on the racetrack there. That certainly is possible. So now somebody said something about the car stopping, but I think there's more to it than this. Take a look at car B. What happened during this time frame with car B? So Calvin, you still online there?
Mm-hmm.
What do you look at this graph? Do you think that car B stopped, or do you think there's more to it than that?
It looks like, yeah, it looks to be like it. Oh, it goes back. Yeah.
Very important. Yes. Car B did not just stop. Car B, maybe it got spun around backwards or what, but for about 1 minute there, car B was actually moving toward the starting line. He was moving backwards. Now, car C, I'll admit, car C was stopped. And now, can we know how much time it was stopped at? So how about, let's go with Taituan. Taituan, can you tell us, looking at this graph, can you tell us how much time car A was at a stop right in here?
It looks like car A was at a stop for about 2 minutes. 2.5.
Yeah, 2 to 3 minutes, right? It's when you're looking at a graph, it's hard to be exact, but yeah, somewhere between 2 and 3 minutes, car A was at a complete stop. All right, so Taituan, you want to take her from here? So let's look at this section in between 15 and 20 minutes. Tell us what's happening. If you're the radio announcer, how would you describe what you see there?
Let's see. Car A was at a stall, but they continued to keep racing. And car C never had any problems and continued to climb and catch up to car A. Car B seems to have crashed and are completely out of the race as of right now, between 15 to 20.
You guys agree? All right, I think he's captured all the important things there. And let's see, how about Will? You get to finish it up for us, Will. So you are the announcer for the last 5 minutes here. Based on what you see on the graph there, Will, how would you describe the race?
I mean, there isn't really much to describe anymore. It looks like car C has been pretty constant, and then it looks like they finished the race first, which is why they stopped.
Well, that's pretty important.
Yeah.
We need to know who won the race.
Yeah, and then car B, maybe the driver's dead, who knows? And then car A came in second, I'd say.
Okay, great. All right, so now we're all assuming that the finish line is at the 25-kilometer mark, which may or may not be the case, but it's a good assumption. So yeah, I'm okay. Let's go with it. So if the finish line is at the 25-kilometer mark, it does look like car C just barely won the race. Car A came in second, and car B, he's just out of it. As some of you are saying in the chat box here, you're suspecting that he's dead or stuck in the mushroom pit. Oh, mushroom it hit. Okay. All right. Okay, so hopefully now you guys can see that the position versus time graph is a wonderful tool. I think it's way better than the motion diagram, you know, the dot diagram. The position versus time graph has a great wealth of information in it. Now, there's also something else that we can pull out of here that nobody has mentioned yet. What if I were to ask you to focus in on these first 5 minutes of the race? And if I asked you to come up with a number that told me how fast car A was going, what would you say? And I'd like you, rather than speaking it into the microphone, I'd like you to type it into the chat box. I want you to type in how fast in kilometers per minute do you think car A is going? I need to see a bunch of answers. Okay. All right, looks like everybody's agreeing that it's 2 kilometers per minute, except Taituan, and it looks like Amy also, are saying that maybe it's not exactly 2 kilometers per minute. And I would agree with them on that, because if you look right here, okay, you'll see that the line, when it passes the t=5 vertical line there, it's a little bit below the 10-meter mark. And when it gets up here to the 20, it's even more clear. When it passes the t=10 line, it's definitely below the 20 mark. So you can see the speed is not exactly 2 kilometers per minute. It's a little bit less. But if we report the answer with only 1 sig fig, it's okay to say that it's 2. Just remember that it's actually a little bit less. Okay, so by looking at the slope of this line, that will tell us the speed. Okay, that's an important thing to know. That might come in handy in tonight's homework. Okay, well, I think we're good on that. Any questions about what we did there? Not hearing any or seeing any. All right. Well, I think that we are ready to start on tonight's homework here. So class period is not over. Just the fact that I'm going to stop the Zoom session does not mean that class is over. Class doesn't end for, oh my goodness, we got more than a half an hour here. So I want you guys to use this time to work on these homework problems. Now, notice what I've done here. Problem numbers 1 through 8, I want you to do all of them. But problems 9 through 17, if you just do the odds, then that's good. And you'll notice what a wonderfully nice guy I am. I could have chosen the even ones, but then the answers wouldn't have been in the back of the book. But because I'm such an incredibly nice guy, that's not a lie, that's the truth. Well, sometimes anyway. Okay, so because I chose the odds, that means you can look up the answers in the back of the book. All right, so do not think that class is over and you can go play now. You've still got at least another half hour here. I want to use this half hour to do this homework. Now, before we go, 2 things I want to do. One is, if you have any questions that you were too embarrassed to ask because you knew that the class was being recorded, well, I'm going to turn off the recording right now. And then the other thing is, if you don't have any questions and you want to leave the meeting, that's fine. But make sure you type bye into the chat box before you leave the meeting. Otherwise, you won't get credit for being here the whole time. All right, I'm going to stop the recording.